Welcome to Networking Field Day. The presentation that you are about to watch from Barefoot Networks is being attended by a group of invited networking delegates who represent the community by asking questions, offering opinions, and discussing the technology that you are about to see. If you would like to see more information about this event, please go to our website, techfieldday.com, and check out our YouTube channel, youtube.com/techfieldday.
I'm very happy to introduce Nick McKeown. He's a professor at Stanford, a co-founder here. He spends a lot of time here. I won't say how much because I'll get him in trouble. And he'll spend some time maybe giving you an idea of why you should care.
Thank you. Great. Thanks a lot. So I think I've met quite a few of you before last year. I'm Nick McKeown. I'm chief scientist and one of the co-founders here. And as I think some of you may know, I'm also a professor at Stanford in computer science and electrical engineering, where I work with graduate students and run research programs in networking. One of the research programs that we started a few years ago was called the Clean Slate program. The Clean Slate program led to what is now called software-defined networking. Martin Casado was one of my PhD students, one of the better ones. He was clearly a very accomplished guy. After a few years, we started Nicira together. You know, I like to think of what we're doing here at Barefoot as a logical continuation of what we started then. So Nicira, software-defined networking, brought to those who own and operate bid networks, it handed them control over the control plane. What we're trying to do here is to hand those who own networks and those who build equipment for them the ability to define the forwarding plane. So it's really a continuation of what we saw before. But I think to really frame what we're trying to do here, it's good to start with a question. And the question I want to ask you is, have you ever stopped to wonder why it is that it takes so long, so many years, to add new features and functions to networking equipment? What is it that's going on that takes so long? Let's start with an example, VXLAN. VXLAN was first defined in 2010 by Cisco and VMware. Let's just look at the steps that needed to take place in order for that relatively simple function to be added to a switch or router. So inside a switch or router, here's a cartoon picture. They all have a switch operating system inside based on Linux or some variant of Unix. And then on top of that, there will be user space processes that are implementing the control for those protocols, OSPF, BGP, etc. And then a driver that is communicating to add and delete entries into a forwarding chip. So now imagine it's 2010. Customers are clamoring for VXLAN, and the switch vendors need to figure out what they need to do in order to add this feature. Well, they've got to be able to add VXLAN there as the means to talk to the outside world and to implement the control of this protocol. They also need to change the driver in order to be able to add and delete entries into the VXLAN tables that presumably will be in the switch ASIC. They also need to be able to update the ASIC. This part up here, few weeks work. This down here, 4 years. It was 4 years until this feature became available in merchant switching silicon. So why does it take so long? Let's have a look at what's going on during that time. So they've got to add that feature. In this case, it's not a niche feature. VXLAN is not a niche feature that you just put on the back burner. This is in the most highly invested in, the most profitable, the bleeding edge part of the networking industry. So let's think about what happens. The enterprise network folks go to their vendor and say, I need this feature. The equipment vendors all get together, gather at the IETF, as they do, in order to try and figure out what is this feature that they're going to implement. They have to go and talk to their software teams, and they'll say, this is the feature we're thinking about, and they'll come back and say, yeah, we can do that in a few weeks. Then they need to talk to the ASIC team or their third-party switch chip vendor. And so they'll say, these are the features we need. They're pretty simple. It's just a table. It's just a new way of processing the packet. And they'll say it's about 4 years, or 2 to 3 years in order to development, add it into a product, and so it's 4 years before they can get this. So it really is kind of a process that is at odds with the rest of our industry. So it means your vendor can't just send you a software upgrade. That would be nice. It takes years for them to develop that new feature, and this is really a simple feature. This is not like we're trying to add anything particularly magical or particularly complicated. It's about as equivalent to, I don't know, reprogramming the hash entries for ECMP, or adding a few extra counters, or changing the way in which the resources. These are all relatively simple. It takes them so long, but probably by then you've figured out a kludge to get around it, because you're not going to wait 4 years for this feature. Adding a kludge is never really a good idea, so you've made your network more complicated, less reliable, more brittle. And eventually, when that upgrade is available, it either is no longer solving your problem, or you can say, okay, I'll go for it, and then you're going to replace all of your hardware, which is expensive, and all the other pains that come with making that change.
Trill. That was Trill.
So, when you look at it like this, the whole process is kind of a little bit crazy. And we've got used to it. We kind of take it for granted now, right, that this is how our industry works. Because we're being fed a line, and we've been fed a line for a long time. And it really is at odds with a lot of the areas of high tech. Let's look at what happens. Let's look at what's going on with this, where this comes from. It all stems from the fact that if you're trying to build a piece of networking equipment, you start by looking at the various types of fixed function switches that are available. They all come with a data sheet, and it says, this is how I process packets. This is the features that I have, the protocols that I support. And then you look and say, well, out of all the things that I would like to have, which one is the closest to meeting my needs? It probably has a whole load of other stuff in there that you don't need, but you look for the one that's closest. And then from there, bottoms up, that will define the system that you can build. So as a consequence, the entire products that you can build today, unless you can fork out enough to build your own chips, are defined by data sheets from third-party vendors. So the features that are being defined in our systems are being figured out by chip designers. So it's not surprising the feature set that we end up with doesn't particularly fit with those who want to operate big networks, because the features are being picked by chip designers, those who are willing to put in all of that complexity into the chip. So one way to think of what Barefoot is doing is trying to turn this model upside down. In fact, the whole P4 and programmable forwarding plane movement is trying to turn this upside down. We want a programmable switch. You'll see more of Tofino later. And we'd like to define the behavior that we want by saying this is precisely how we want packets to be processed in a program. This is a snippet of a P4 program. And then we want to compile that and then drive it down in order to tell the chip that this is the behavior that we want. It seems actually kind of obvious, right? I'm belaboring the point here to try and make it very clear, but shouldn't it always be done this way? And in fact, it begs the question, why aren't all network systems built this way today? As soon as you see it this way, you kind of can't unsee it, because it makes you ask the question, why doesn't everyone do it this way? And it took us a while to really convince ourselves, and we would ask the question a bit timidly to start with, then say, are we being silly? But there's this conventional wisdom in networking that you hear time and time again. And I've heard this one for 20, 25 years. Programmable switches are 10 to 100 times slower than fixed function switches. They cost more, and they consume more power. We've all heard this. Well, I can tell you that with going back and thinking about the basic operations that you need for networking, the instruction set, the data models, the way that ASIC technology is evolving, we can say categorically this is not true. And in fact, we can say with confidence, and we will show it to you with Tofino, that you can build a chip which is as fast, does not cost any more, and consumes no more power, and is programmable by the users who build systems out of it. Tofino operates at 6.5 terabits per second, and Tofino is the fastest switch chip in the world, and it's programmable by its users. To put in context what 6.5 terabits per second is, just because I think it's kind of fun, if you were to watch the entire Netflix catalog from now, it would take you 4 years to watch that catalog. Tofino will switch it in 20 seconds, that entire catalog. Okay, any 6.5 terabit per second switch can do that. Tofino will run a 4,000 line program on every packet it passes through. It costs the same as a fixed function chip. It consumes the same power. It's easy to program. It's easy to program in the following sense. We have had users who have never heard of P4 before. They learn about it. They learn to use it. They write a program. They contribute it to the repository in less than 8 hours from beginning to end. So it's not something which is for really deep specialists who know a lot about a specific chip. It's a general way. It reads like common sense.
Where is that repository?
P4.org. P4.org we'll talk about a little bit later. So why is this happening now? Part of it is this garage. But there's another reason that it's happening is that networking is kind of catching up. It's catching up with what has happened in other areas of IT for a while. We're all very familiar with this model. We write high-level programs for our computer. We've all done this, Java, Python, C, whatever it is that we prefer to use. We run it through a compiler. It runs onto a chip below. It's important to note that that program up there, written in whatever language you prefer, is compiled down to the target without you having any knowledge as to how that compilation takes place. Down here could be x86. It could be an ARM processor. It could be AMD. You don't care. So you're writing in a target-independent, portable fashion. What some other domains have done is develop their own domain-specific processors with domain-specific languages that are specific to that domain. OpenCL for graphics, for example, compiled down to a GPU. I don't know if any of you are old enough to remember when graphics cards were these big fixed function cards from Sun and HP and DEC. At that time, there was a raging debate as to whether anybody could ever build something that was programmable that would be fast enough, low enough cost, and low enough power. Along came the GPU, game over. You would never go back. What they did was figure out a basic instruction set and a data model that they could build that domain-specific processor for graphics. And so if you want to define a renderer, this doesn't know what rendering is. The rendering is defined up here. Same thing happened in signal processing. It used to be that in order to build a radar or a base station or something like this, it would all be fixed function hardware. You wouldn't dream of doing it that way today. The DSP from TI and from others running at multiple gigahertz was a domain-specific processor for signal processing. It doesn't know what an FFT is. You tell it what an FFT is. And you tell it in a language, high-level language like C or MATLAB, it's compiled down. Domain-specific language, domain-specific processor. You get the pattern. Same thing happening in machine learning. Domain-specific language, domain-specific processor. That's all happened in the last year. So what about networking? Who skipped networking? Right? So what happened? So we don't have a common language until now, and we certainly don't have the domain-specific processor, which is a target for such a language. And that's what we've been building. So the language is P4. It's not necessarily the only language. It's the one that is gaining traction right now. It's a domain-specific language for describing how packets should be processed in a network. There is a compiler that will compile it down to run on a particular class of machine. And the machine that we're going to be describing today is the architecture we call PISA, P-I-S-A, for protocol-independent switch architecture. The switch itself does not know what a protocol is. You'd think a switch would know what a protocol is. But the key here is just like a graphics device doesn't know what rendering is, this doesn't know what a protocol is. The protocol is defined here. So if you need to add a new one, you change the program. If you want to throw one out, you change the program. And then you compile down to run on here. The first instance of a PISA chip is Tofino. So it's an instance of a PISA architecture device. To understand, yes, go
That
ahead.
implies, that sort of implies a couple of different things. One is you might expect other languages from P4 to emerge, and you also might expect other silicon below the line to emerge as well. Is
Correct.
that a fair assumption?
Yeah, absolutely.
Once we've proven out.
Absolutely.
And a follow-on question, if I may. We have GPUs, we have DSPs, but the market size for those is enormous, right? You know, measured in, you know, hundreds of thousands of units of shipments per month, et cetera, et cetera. Networking is a relatively small market, like in terms of units shipped, the number of switches that we actually use. And if the market's not big enough, the market mechanics may not make it viable. Is that a concern, or do you believe the market is viable?
We're very comfortable with the business opportunity for Barefoot and the space in general. One way to think about the market is just to think about what goes on in a data center. While one of these devices may be comparable to the bisection bandwidth of the public internet, inside a data center with, say, 400,000 servers, there'll be 20,000 switches inside that.
Right.
And there are a lot of data centers being built. So the market size here is easily enough to support several players. So we're not worried about that. But we do expect that there will be, over time, there could well be other languages, there will be other devices. Really, this model levels the playing field. So instead of hiding behind closed lock-in strategies, no one can get access to our API, for us, it's all open. And so that we can bring on this programmable model. So in order to understand how this works, it's good to go back and look at how the fixed function switch chips work. This is an example of a fixed function pipeline that will be pretty commonly used today. Arriving packets, they arrive to a fixed parser. That fixed parser has been told at the time that the chip was designed what set of packets that it could recognize. Once it's recognized them, it'll pass those headers along to each individual stage. Here we see Ethernet MAX, MPLS, IPv4, ACLs, whatever happened to be designed in at the time that the chip was first built. The first stage will process this. It will pass it along to get processed here, down the pipeline as it goes. If you want to add a new feature, like my VXLAN example, you need to insert it in here somewhere, but there's nowhere to put it because it's all fixed at design time. So there's no way that you can do that. Even if you're not using MPLS, as most people don't, you can't say, oh, I'll use that resource that. You can't move the resources around. Or even you say, hey, they put too many prefixes in there. I want to take some of that space and use that for VXLAN. You can't do that. You can't even get it to recognize a VXLAN header because it wasn't told about that at design time. So features and table sizes are baked in at design time. And essentially, this is the way that it's been done for 20 years. This is the way it's been done for such a long time. You have to ask the question, surely one area of tech cannot stay unchanged for 20 years.
So I have a quick question about that. So what is your table size? And you may be covering this later, but that leads to being able to allocate it wherever you want. What could the table size be of a Tofino switch? Yeah,
so the table size overall is really determined by the physical dimensions of the chip, and all of these chips have the same physical dimensions. So we will end up with Tofino as being able to 1 to 1.2 million prefixes.
Okay.
If you were to only use it for that purpose.
Right.
Then you can then choose how you use that resource.
Okay.
So if you wanted to claw some back for IPv6 or for something else, you can do that.
So it's
we'll see an example
dynamic
of that
allocation
later.
for you. You just make that choice, and that's where I want
exactly.
to go. Yeah.
And if you want to change it while it's in the field, you can do that.
Okay.
So we'll see an example of that in a demo later.
Okay, cool.
But it allows us to have one hardware platform that can suit multiple needs.
Exactly. So you can have it that you can change it, you can upgrade it. In a sense, what's happening is Tofino is bringing you peace of mind. We're a peace of mind company, right? You can change that later in the field. And in fact, you can do things like, I want to put a layer 4 load balancer into my top of rack switch. Just download a new P4 program, add it into that, and upgrade that feature.
I want to step back for a second to the fixed process or fixed architecture versus a programmable architecture. It was common knowledge, right? That fixed process would be faster by orders of magnitude.
Yes.
And you're saying that's different, but why? Is it because the conception was wrong? Or is it because technology has changed that's allowing us now to have a programmable architecture that's better?
I would say that as an industry, we were lazy.
Okay.
If you think about what happened with the GPU came along because a few folks stepped back and said, I'm not going to try and modify a CPU. I'm going to say, what is the instructions that I need? What is the parallelism model that I need internally? And they knew enough about graphics to be able to figure out how to do that. In the last 10 years, partly because of SDN, disaggregation, etc., we've got a much clearer idea of what is it that the forwarding plane does in a switch. And this match action paradigm, match on headers followed by an action, has really arisen as a common abstraction for the way in which packets have processed. So now you need an instruction set that will allow you to declare what am I going to match upon and then the actions that I will perform. And if you can get the right instruction set, and Tofino has on the order of 1 to 2 dozen instructions internally that the compiler will use in order to process the packets. It's really spotting what they are, figuring out the right model of parallelism to bake into the chip. And that was the thing that happened before. People tended to say, I'll build a programmable device by throwing lots of CPUs down onto a piece of silicon. That's not architecting for the common, for the specific domain of networking.
So you think we just become more intelligent about the way we've narrowed down the instructions
it's
that
sort
a
of-
network processor
exactly.
has to do?
That's right.
Okay.
That's right. And really following the lead of the GPUs and the DSPs, because they kind of did the same thing. So this is the sort of the simplified figure of the PISA pipeline. The thing to notice here is that each stage is identical. I show 4 here just because that's what would fit on the PowerPoint. In practice, it could be 4, it could be 15, it could be 20. So but you should think of it in terms of roughly a dozen stages. Each of these is identical, both in terms of what it does and its dimensions. Each one is implementing a match plus action. There are multiple match memories here, so it can do multiple matches on different headers at the same time. And then once it's matched upon them, it can perform actions from that instruction set that I described earlier. So that's done by these ALUs that are here. Okay? So multiple matches, multiple actions, and then move on down the pipeline. Initially, it doesn't know what a single protocol is. We have to tell it by the way in which we program. First, the programmer has to declare which headers are recognized. That's described in a program. And so it will download in here and say, these are the headers. So if I want VXLAN in there as well, that's what I would place. That's where I would place it. Next, the programmer declares what tables are needed and how the packets are to be processed. So all the stages here are identical, and we have been adamant about keeping them identical, simple, uniform, because this allows the compiler to have a very simple view of the underlying compiler target. So we use a term here at Barefoot. We say we're building a compiler target. And so long as we can keep in our minds we're building a compiler target, then we can make sure the compiler can do a good job. Let me just elaborate a little bit more on what's going on here. Imagine there's a packet coming from the outside. The little colored squares at the beginning are just different protocol headers. What the parser is responsible for is ripping that apart based on the description we've given of the headers that it should recognize, identifies the headers, and then it's going to pass them down this pipeline. And the way to think of it is that each stage of this pipeline is going to perform a transformation of this set of headers. So for example, the first stage will do match plus action, and we end up with a different set of header fields. It could add some, like pushing an MPLS tag. It could modify them, like decrementing a TTL in an IPv4 header. So that's a transformation that happened here, and then it's going to go down multiple transformations as it goes down, matching, action, and until it gets to the end, and we end up with some modified set of headers as a consequence of the program that we've been told to run. At the end, these get put back into the header, queued until it's turned to leave, and the normal packet scheduling algorithms, and then it departs. So from the use, yes, sorry, Greg. Yeah.
Sorry, I'll be very quick. The header is what's being manipulated here, not the payload, not the data, just the header actions.
Correct. You should think of the sort of the PISA and P4 approach is about the headers. Now it all begs the question of how much header can you look into, and that's an implementation specific choice, but it's thousands of bits of the order of 4,000 bits of the header.
Because I'm thinking in terms of an IPv6 header, which can get quite large.
Yeah. And so this is sized to make sure that for anything that you could sort of imagine as a header.
Yep.
So if you imagine it was 4K bits wide, for example, that's an awful lot of header that you can get.
Yeah, well, yes, it is. But the point is it's programmable, it's staged, but we're manipulating the header. We're not doing layer 7
That's right.
activities here.
Correct.
We're doing L3, L4.
Correct. Or encryption for that matter, which would require looking at the entire payload.
Yeah, that's right. So that's the limit, well, not the limit, but that's what this is intended because and I guess I'd just like to clarify this, because you're forwarding at 6.5 terabits per second, you can't afford to be doing L7. You've got to pass this through.
It's really just a trade-off of bits per second versus packets per second. So there's a certain part of the processing which is packets per second. All switch chips have to make this trade-off and trying to figure out how they're going to find the sweet spot of both. And so in order to do that without consuming too much power, most go for processing the headers, but not the payload.
Is that an evolutionary path in the decades ahead?
I would fully expect that there will be switch chips that will be P4 programmed that will do payload processing. But whether we see them at the very high end remains to be seen.
Yeah, but it's an evolutionary path that might reasonably expect to see, line rate forwarding at very low latency doing L7 with a programmable architecture.
I would expect so. You might not see it yet at the very top speeds, and it will probably always lag a little bit behind because it consumes more power and has more processing.
And I think it would also be fair to say that's years away. That's not this year sort of thing.
Yeah, I would expect in the There was another question over here, yeah.
Before the animation, your slide said the programmer decides what tables are needed.
Yes.
Does that mean the programmer is choosing from some available list of tables, or he's defining the tables that?
And even the names and what they mean. So it might say, hey, I want IPv4. I want a table that's a VXLAN table. I want it, right? I may say that. I actually might design my own, if doing some crazy experiment, IPv-NIC, and I actually want to describe my own type of table. Maybe it has 33-bit headers instead of 32-bit.
The tables are from the programmer's imagination.
So they're from the program,
not from the hardware.
That's right.
Thank you.
However, for the purposes of getting people going, we have built and then actually open sourced a lot of libraries for things like IPv4, IPv6, all the common types of protocols.
Sure.
Just to get people going so that they can get a starting point. But people wouldn't remove them or edit them and change them if they want.
These targets and transformation points, is that like a hardware limitation? How many you can go through, or is that
how many stages?
Yeah, how
There's
many
a fixed number of
stages?
stages in a machine.
Okay.
Yeah, and we'll talk more about the insides of Tofino a little bit later.
Okay.
But that will be a implementation choice for a particular PISA chip. The only reason for 4 here is a PowerPoint limitation.
Right, but I figured there had to be some.
Yeah, there will be a physical limitation
Yeah.
in the machine. Yeah. So from the user's perspective, I write a program. There's my snippet from earlier. It's got a type of table that I described here, and then a type of processing. I'm not going to go through the details of that. And that program is then compiled down and loaded onto the chip. Right? So while that magic is happening underneath, the user should be about as familiar with what goes on in here as you are about the insides of an x86 when you're writing a Java program. The idea is to shield as much as possible. However, make it available to them if they want to see exactly what's going on. So in terms of the way in which they get mapped, one mapping might be I put my Ethernet MAC table here, my MPLS, I put my IPv4 over here, and I've noticed that I don't need to do the ACLs at the end of the pipeline. I don't mind the order in which I put them, so I put them here. That would be one example of a mapping. The compiler did that for me based on information that I gave it. If later I want to be able to make room for IPv6, I can just shift up and insert IPv6 in there. I may, in fact, go back and say I want my VXLAN feature, so I just use that unused match action capability right there. Okay, so I've given you a view of this programmability, roughly at a high level how it works. In a few minutes, Dan is going to go into more detail of how Tofino actually does this more specifically. But you might be sitting there thinking, okay, Nick, I kind of believe that you could do all of this. But remind me, why would you do this? Why would you make it programmable? What are people actually going to do? I think you'll get an idea during the afternoon of some of the applications. And we've gone through and talked to many, many people about the applications that they're interested in. But there is one, I'm going to call it the killer app, the one that we just keep hearing again and again and again. It'll come as no surprise to you that it's about visibility, it's about telemetry, it's about knowing what's going on in my network. Before I tell you about it, worth telling a little story. I say that tell the story sometimes. It's a story. We were visiting somebody on Wall Street, and the meeting was delayed. And they told us the meeting was delayed because they had an outage in one of their data centers. And what happened was they were losing millions of dollars a minute or an hour. I don't know how much they were losing. They were clearly panicked. They put 2 compute people in a room, 2 networking and 2 storage people, and they said, okay, you need to figure it out. Within 30 minutes, the compute folks, they were trying to isolate the problem. They had measurement going on. They were trying to repeat the problem. They were doing workarounds. They were programming. They were running in the real system. The storage people, almost the same, not quite as flexible. And the networking people were sitting looking very bashful because they had ping, traceroute, and SNMP. It's the same measurement features that they had 20 years ago. Nothing had changed. I mean, it's pretty shocking. And so I like to say, the philosophy of making networks today was brought to us by Yo-Yo Ma because you're on your own, mate. Right? Basically, what we're doing. I mean, I think we should be kind of embarrassed at the state of measurement in networking systems. Because when it comes to debugging a network, what is it that you really need? You don't want sending traceroute packets that are different from your data packets that take different paths and experience different queues. You don't want pings that don't really tell you anything at all. And you don't want SNMP that's averaging over long time periods. You never really know whether it's doing it right. What I'd like to be able to do is very simple. I want to go into the network, I want to pick out a packet, and I want to look at that packet and say, why are you here? How did you get here? What delay did you encounter when you were getting here? And if you got here slowly, who got in your way? There is no network in the world that can come even close to telling you that today. So let me turn this into a small set of questions that we would like to be able to answer. So imagine I'm in my network. There's two racks of servers that are communicating together. And I'm going to go in, and I'm going to go to one of these packets, and I'm going to say, which path did my packet take? Right? If I can get this ground truth, this is certainly more than I can get from any system today. I'd like the packet to say, I visited switch 1 at this time, switch 2 at this time, switch 12 at this time. That's what I'd like it to tell me. I'd also like to answer this question. Which rules did my packet follow? As it went through all of these switches, there was a set of tables, like prefix tables. So here I matched on rule 75 for this particular prefix. I'd like it to be able to tell me from that packet, I followed these particular rules. So I know the path it took, the time that it got to each switch, and the rules that it followed. It's kind of obvious. My CPU will tell me that about my programs. Why can't my packets tell me that about my network? I'd like to go further. I'd like to say, how long did my packet queue at each of the switches that it visited? I'd like it to say, I was delayed this much at the first one, this much at the second one, and whoa, this much at the third one. There's a problem. Okay, I see the problem. Now I want to try and diagnose the problem. So I go to the switch. I want to be able to do this and say, give me the time series, the entire time series of the occupancy of your queue, right down to the packet, right down to the nanosecond, and tell me what happened here when the delay suddenly went up. There was congestion. Was it my fault, or was it somebody else's fault? I'd like it to be able to tell me, who did my packets share the queue with? In this particular case, it turns out I was the green one. I was perfectly well behaved. The orange one was the problem. I'd then like to go and say, there was an aggressor flow over here that was sitting there and then generating a whole load of packets. These 4 set of questions, if I knew them, will give me ground truth about the behavior of my network. Which path did my packet take? Which rules did it follow? How long did it queue at each switch? Who did it share the queues with? So there is no network in the world that will tell you this today. But I can tell you this. In fact, we're going to show you this. Tofino and P4 can answer all 4 questions for the first time at full line rate without generating a single extra packet. So once you've got that information, you can go and find out everything about the behavior of your network. So look for that a little bit later this afternoon. So to come back to why is it that someone would do this, you're going to hear us talk about this because we ask ourselves this a lot. We want to always remind ourselves of why is it that someone wants programmability. They want to add new features. If they're in a data center and they've got some new clever idea, or if they're a large enterprise and they've got some ways to build their network better, they might want to add stuff. They might want to subtract stuff. They want to remove things that they're not using to make their network more reliable, or to free up resources for some other purpose. And the last thing is that they want greater visibility, as I just described, into the way in which their network is behaving. Any last questions before I wrap up?
One thing that I wanted to ask earlier was, as you push new, we'll say, features down to the chip, how does that affect the forwarding of packets? Does everything stop? Does everything that's not in the tables, I guess, how does that, what's the effect?
Sure. So there's a few different answers to that question. In principle, with this model, with this PISA model and programmability through P4, in principle, nothing needs to stop. You never need to drop a packet. There's nothing in the approach that would do that. It all comes down to the particular implementation of the chip and the particular implementation of the compiler. In the worst case for Tofino, if you wanted to change the entire program, reboot, and come up, it'll take you less than 50 milliseconds. That would be in the worst case. In some cases, you can actually change it on the fly without actually bringing it down. It'll actually depend on what you're changing. Imagine you've got a long pipeline and you switch the order around completely. That's a bit too much. So it would take you 50 millisecond hit. But there's nothing in the approach that would mean that you couldn't do that. It's just a choice that you make at the design of a particular chip or a particular compiler.
You're adding your VXLAN example.
Yeah.
That probably would not be would interrupt service, would it?
It depends whether you had left room for expansion at the time that you did the design in the first place. So it's a
Assume
sort of
you did it correctly to begin with.
That's right.
Yeah.
That's right. That's right. Yeah.
I don't know if this is the right place for this question, but by opening up the chip for programmability, you're also potentially adding the need for some kind of configuration management, change management infrastructure. Is that something you guys are thinking about?
So it depends on, you're absolutely right that you obviously need to think very carefully before changing your network. For the majority of users, we would expect this to be done by the equipment vendor. Right, so a large fraction of our customers are equipment vendors who then handle that with their customers. They may be done through quarterly revisions and updates. It may be done through different profiles for different customers. That's up to them to figure out how to do that. And in a way, it's very much in keeping with the way that firmware and software upgrades would be done today. So that'd be one approach. For the MSDCs, who are of course our other customers right now, they have their own ways of doing this for firmware and software. We'd expect it to fit in with that. So as they're doing their upgrades, we're a little ways away from somebody who is doing this in a relatively small environment for themselves. There is no reason in principle, but we fully expect that to sort of develop and come out over the next couple of years, that more and more people will be doing this for themselves with disaggregation and white boxes. But that's sort of beginning to play out now. In the early days, we would expect this to be largely done by the equipment vendors.